Okay, so I remember we began to talk about RISC computer, right? So what does RISC mean? RISC stands for Reduced Instruction Set Computer. But my question is, what does that mean? Do we really want to reduce the number of instructions? Is that the sole purpose of designing such a computer? Doesn't sound like it. What's the true purpose of a RISC? Tell me. So, we often heard people say, we design RISC before we want to get more performance. Okay? Some people make that statement even easier. RISC is designed for performance. If we say RISC is designed for performance, then does that mean CISC is not designed for performance? CISC stands for Complex Instruction Set Computer. That's a misconception. All computers are designed for performance. But some may be a better design philosophy for performance. Some may make the machine more difficult to achieve higher performance, right? So let's take a deeper look into RISC design. Number one, RISC stands for Reduced Instruction Set Computer. And I don't like that name. The name I like better may be regular. When they come up with a name, the name should make people easier to remember, right? So maybe they use the word RISC for that purpose, but I think regular is a better name for this kind of computer. And they said RISC is designed for performance. So my second question will be, performance comes from where? Performance comes from where? Do you know? Where does the performance come from? From several things. But one key word says it all. Performance comes from pipelining. The answer is pipelining. Now, can you be persuaded that pipeline can enhance performance a lot, very efficiently? Can you? Why is that? Because during the life cycle of an instruction, it usually will have to go through fetch, decode, execute, and some may need to access memory and put the result somewhere before it goes away. Okay? Most instructions do this. And if we can regulate all the execution flow of the instructions and make them pipelinable, can you see the speed up? It's n times speed up right away. And this seems to be easily achievable. Okay, so how can you make pipelining possible? Number one, make fetch easy. Number two, make decode easy. Number three, make execution easy. Number four, make memory access easy. And number five, make this easy. Usually we can divide the execution flow into these 5 major stages. Make them easy, also make them take about the same amount of time. Okay? And then next thing is to make them use different resources. Different resources means let them take place in different timing points. Let them use different circuits and whatever. Okay? So, how to make fetch easy? The answer is make all the instructions of the same length. Right? If you can make all the instructions of the same length, then the fetching is easy. I can even say I want to fetch any instructions at a time. Easily. Okay? How to make decode easy? How to make decode easy?
Same number of operands.
Make the instructions all have a known format. Better be fixed format. Okay? So how many bits do we have? We have 32 bits. Or fixed number of bits. The most popular instruction length is 32 bits, right? Anyway, it's fixed. Fixed for easy fetch. In addition to that, all the fields are of fixed purposes. Whatever. No matter how many fields you have, they better have fixed places and fixed meanings, such that when I decode this instruction, I in fact use a number of independent circuits to decode them. What do you mean by decoding? It's nothing but bit string transformation. Every of these is nothing but a Boolean function. Right? What is decoding? According to your bit pattern, I translate into control bits. Okay? So decoding is nothing but a Boolean function. And if all the bits are independent of each other, then I'm using a group of independent simple Boolean functions. Remember Boolean functions? If you have 10 inputs, then you know the Boolean function circuit may be huge. Latency may be too high. Okay, so I cannot use more than like 8 bits, 6 bits for each individual field. Okay, so now do you know how to make decoding easy? You do. How to make execution easy? I allow only primitive operations such as AND, OR, add, subtract. I don't give you any multiplication unless I can make the multiplication accomplished as fast as an addition can. Okay, so you want multiplication? 2 approaches. Number 1, take multiple cycles, make it an exception, and disrupt the pipelining. Or number 2, make it fast so that it will go smoothly in the pipeline with all other peer instructions. Okay, 2 approaches. Which one do you prefer? Depending on whether you care about speed or the cost. What about memory? Okay, we in RISC design treat memory accesses as exceptions. You always need to go to memory. But you hate that because it's so different from all other instructions. Okay? Why do I say other instructions? Because the others are the majority. And instructions going to memory are the minority. How minor are they? Well, really they account for almost about half of all the dynamic instructions. So they are not really very minor. Okay? They account for about half of the dynamic instructions. let's say 40%, okay? So there's still the minority. Okay, whenever you have a result generated, the result needs to be written back somewhere. And we say that somewhere will have to be registered. You never can write back to memory. So when we say write back, we say write back to register. Do you need to write back to memory? Okay, I treat that as an exception and handle it in this stage. So if you have a store instruction, then that instruction ends there. It doesn't use the write back stage. Okay. What about if you have an add? Then you use these stages and you don't use memory stage. Okay. And if you're using loads and stores, well, I told you we don't use this stage. But what about this stage? Do we need execution stage for the loads and stores? Oh, yes, if we do, then we can have more addressing modes. We can play with those addressing modes, like index, base register plus offset, or base register plus index. When do we do the plus? The addition is carried out in here. Okay? So for the load type instruction, particularly these load type instructions, I use all stages. Fetch instruction, decode and find out it's a load, and then calculate the effective address, and then go to memory to get that piece of data, and then put it back into a destination register. So the load instruction uses all 5 stages, and almost all other instructions that you might know of use less than 5 stages. Any questions so far? Okay, so we hate to go to memory, because once we need to go to memory, first, it's a rare case. Secondly, or most importantly, whenever you go to memory, memory is slow, remember? Memory is slow, so we hate to go to memory. These days, we begin to have a cache memory. Since it's expensive, so we use $sign to stand for cache memory. These days, we have cache memory. How fast is the cache memory? Well, I can make it as fast as the processor, on the condition that it cannot be too big. So if I have a processor and give it 2 caches to use, one cache for the fetch instruction and the other cache for the loads and stores of data, right? Code access, data access, right? And when you pipeline them, then every memory access will conflict with the instruction access. And 40% of the chance you'll get conflict, right? So it is a better idea to have both caches to avoid these conflicts. Okay, so usually we give it 2 caches. One is instruction cache and the other is data cache. And these 2 caches cannot be too big. Usually smaller than 64 kilobytes. The most typical value is 32 kilobytes. 32 kilobytes. And then we have a second level cache if you think this space is too limited. So the second level cache, L2 cache, usually is mixed or unified for both code and data. And the size of this level 2 cache is not a concern. These days can be 1 mega. Okay, can be certainly much greater than these two. But these sizes of these two are always constrained because these two need to run as fast as 5 gigahertz processor. Okay, so we talked about almost everything. Now, let's continue. We know that the instructions should be of the same length. We know that the instruction better have the same formats. We know that all the allowed operations better be simple enough. Okay, and we know that the cache should be accessed fast. And 2 caches are preferable, even though some low-end processors nowadays still use only 1 cache for both the instruction and the data. But these are for cost performance designs or cost designs. Like the cell phone, a few years ago, we still have 1 cache design. Okay, and then the register must be able to be written and read in 1 machine cycle. Okay, when we say machine, we refer to processor cycle or machine cycle. Okay, so let's go to maybe the foils. Don't let's sit there for too long. Okay, we should be done with this page. Next page. Typical RISC ISA instruction set architecture. Now you understand why we have fixed length instructions. And now here we talk about fixed format instructions. Okay, but that's too constrained. So we still allow some flexibility. For instance, suppose this is the OP code. Then we have source 1, source 2, destination. Oops, sometimes we like to use immediate data, right? So perhaps we swap their locations. Put destination first, and then source 1, and then source 2, which may be a register index or immediate, depending on what the opcode says. Okay? So there's little flexibility. The last field can be S2 or, the last field is S2, which can be only that long if it's a register index, or it can be longer if it represents immediate data. Okay? Sometimes we don't need 2 sources. Sometimes we don't need a destination. Tell me, which ones don't need a destination? What instructions don't need destination? Branch. I just want to see if a register content is 0 or not 0. We need only 1 register. Or store. I don't generate any new result, so I don't need a destination. Or this or that, like a compare instruction. I just want to see the relative magnitudes of 2 operands. I don't need to generate any new result other than the flags. Okay, many instructions don't need destinations. So can we use the unused destination for other purposes? Possible. Okay? Possible if you want. Okay, so we understand this now. Why we have some flexibility here, and then we need many general purpose registers. Now tell me, what do I mean by many? That's what the typical textbook would tell you. Why do we need many? Because going out of the processor is treated as an exception. We don't like to have those things happen, right? What's the risk of going out of the processor? Tell me what's the risk. The caches may miss, okay, which incur long latency. Okay, we don't like that. So we try to avoid that as much as we can. And if that's our purpose, then it becomes necessary that we have enough internal data buffering capability. I need to have workspace inside, right? That's why we say we need to have many, many registers. And these registers better be general purpose. In other words, every register can serve any purpose, no restriction, okay, making the work of the compiler easier. Okay, if this register must be red, that register must be green, that register must be blue, and this instruction wants a yellow register. Oh, troublesome. Okay, so make them general purpose. The more, the better. Do you take that? Never. Anything should have a limit. So, what is the limit? On one hand, the more the better. On the other hand, wow, if the register file becomes huge, then it may take even longer time than the other stages. Okay, that's one thing. The other thing is, if I have, say, okay, nowadays, most people have 32. What if I design a 128 register machine? Can I advertise on that? Hey, I have more registers. My machine is definitely going to win. But here comes the trouble. 128, how many bits do I need in order to index those registers? 7. Okay, so one destination takes 7, 7, 7. These three take 21 out of 32, leaving only 11 for other purposes. Not enough. Then your number of instructions will be compressed. Okay, so it's never the more the better. There has to be a limit. First, timing issue. Second, circuit complexity. Third, you've got to leave some room for the others. Right? Right? So conceptually, the more the better. And designers also found that if a register contains 0 all the time, hardwired 0, that can make programming much easier because the constant 0 is used very often. And according to the format, even though this instruction does not need destination, but usually the hardware will overlook that and always generate result and write it into somewhere. Why is that? Maybe that can make my circuit design easier. Okay, there are always dirty tricks to play. Okay, if that can save you some design burden, can make your performance even higher, I like that. So designers say, I need a hardwired register which contains 0 all the time, such that whenever I need a 0, I don't need to access so many bits from the instruction, route them to the ALU. Okay, that takes too much area, silicon area, and sometimes I have some trash to dump. If I need a trash dumpster, make this my trash dumpster, dump it into here. Okay, it will have no effect. So my trash just disappears immediately. Okay, and then when I need double precision, I can use 2 such registers. This double precision doesn't have to mean floating point double precision. it could mean Bill Gates' fortune. 32 bits is not sufficient. Okay, let's go on. For arithmetic expressions, the most natural and general purpose arithmetic expression is result is equal to source 1 up source 2. We rarely use yet another up and another source. Rarely use this format. So in case you need this, break them into 2 instructions. Or use 2 expressions from the mathematics view. Okay? And if you have only 1 operand only, then the type of operations you can perform is still limited. Okay? Or you may say, my destination is equal to myself, OP, yet someone else. Okay, this is general purpose enough, but then your source is limited to be the destination all the time. So it's not general purpose enough. So this is the most desirable format. That's why RISC says 3 address. 3 address means 3 operands. And register to register. For most operations, everything should take place internally. So all the sources plus the destination will have to be registers or will have to be within the CPU. Cannot be memory locations. And then these are the this is the restriction for arithmetic type instructions or large ALU type instructions, arithmetic or logic type instructions. And for the memory type instructions, we allow only limited addressing modes. Most textbooks say limited addressing modes. So when I say limited addressing modes, what will come to your mind? Limited addressing modes.
Fewer operands.
What?
Fewer operands.
No, what will come to your mind should be then which ones. Right? Okay. You don't see eye to eye to me? So tell me which types, which addressing modes. As long as I don't use many, that's okay. Remember, I told you most textbook says few addressing modes. Okay. What does it mean by a few? Limited in number or limited also in type or not limited in number. When I mention a few, that's a misleading word. You think should be limited in type or in number? Tell me. Okay, somebody said type. I just want one word answer. I don't want any reasoning. Don't give me those garbage. Limited in type or limited in number? Type. Any different opinion? Okay, so let's see. Speak up. In number. Okay, so let's see what's the answer. Okay, you both are right, but I want to know who is righter. Okay, so we still remember pipelining is the ultimate goal. Okay, so whatever addressing mode you want to use, the addressing resolution must be accomplished in one cycle. Otherwise, you lengthen the pipeline only for yourself, which is bad. Okay? So, as long as it can fit in the pipelining, condition number 2. You're given only that many bits for the instructions. So condition number 2, as long as it fits in the instruction. Okay. So now tell me if it's limited by type or number or both. More by the type. Okay. But also limited in number, because even if we don't care about the pipelining, still we cannot fit in too many. Okay. While for addressing modes, there won't be too many. Usually 20 is more enough. Okay, even for the CISC, there are about 10 or so addressing modes. But for the RISC, usually we allow for only 5 or so addressing modes. And for the data memory access, we allow for only 1 addressing mode. Usually, I don't say that's a must. I say usually we allow only base plus displacement. And also I emphasize that's only for data memory access. What about for instruction memory access? What about for instruction addressing mode? Okay, let me give you one more piece of information before I go on. According to what I have told you just then, tell me what is the most popular addressing mode? Well, most of you might say the most popular is direct. Right? Direct addressing mode says, in the instruction, I directly specify the address for the load store. Right? That's the easiest one for undergrads. But tell me if RISC can use direct mode or not. Can RISC use direct mode? The answer is always yes. I'm sorry, I need to give you some assumptions before I ask you this question. This question is if the instruction length is 32 bits, and also the memory space is 2 to the 32. Then can we use direct mode? Now the answer is no. Because if I use it, then the address itself will fill the instruction completely. No more bits for other fields. Okay, so now you see in RISC, direct mode is so constrained, I didn't say it's impossible, but most machines don't use that. Okay, because for today, even for 32-bit instruction length, the memory space is already 64. Okay, so direct mode is very difficult in RISC design. Now, back to the instruction access. The instruction access addressing mode, tell me, can we use direct? According to the interpretation, you think value in PC is your direct address. Okay, value in PC, do you think that's your direct address? Well, yes, or maybe not. But anyway, we do have PC relative, right? Instruction fetch is always PC plus 1, or branch PC plus offset, okay? Or this or that, okay? Or register mode if we have a link register to branch to wherever. Okay? So now you understand the addressing modes. Here the author says no indirection. In other words, when you fetch memory, whatever is fetched is the genuine address. That's the so-called indirection. Okay? Do you think indirection in RISC is allowed? Can it fit in the format? I just said direct is not likely. What about indirect? the cousin of the direct addressing mode. Is it allowed in the format? Is it? Is it? Is it? Yes, of course I can use register indirect. Okay, we must. This is a kind of register indirect with displacement. So no indirection is somewhat misleading. Okay, or if I mean into memory and then into memory again, that kind of indirection. If that's that kind of indirection, tell me if it's allowed from the instruction format view. Yes, just change the opcode. This guy doesn't understand what the indirection means. The indirection means the genuine address is hidden in the memory.
Correct.
You need to fetch it, and then you get the real address to fetch the real data. Okay, so in format-wise, it's allowed. You can fit in 32 bits. Okay, but how come we don't like that? How come we don't like that? Because if we do so, then we need yet another stage for memory, for the second memory access, disrupting the pipelining again. Understand? Okay, so you need to think. Don't just read, memorize. No use at all. And then simple branch conditions. Why? Because the branch condition will have to be resolved in execution. Better yet, because branch determines which next instruction it should be. So we want the branch condition to be resolved even earlier, or even earlier, as early as we can. So the branch condition must be simple for easy and hence maybe earlier resolution. The earlier branch resolution enables streamlined effective instruction fetch. Okay? And then delayed branch, this is complicated. I need to draw you a picture to explain that. If I have an instruction execution stream, and if this is a branch if, so as a result, I may continue execution from here or from here, depending on the branch condition, right? Okay, troublesome. This is the branch if instruction. The branch condition is resolved here. So here I fetch in +1, +1, +1, and eventually perhaps the target instruction because I want to branch. Very sad. These three are useless. And you spend time, effort to do them. And even worse, they're already in you. You need to clean them up. Okay, very troublesome thing. So compiler writers begin to think of something to deal with this situation. The method they come up is this. Okay. This is my branch if instruction. Before this instruction, I may have some other instructions forming a basic block with a branch if instruction. Now, I define what a basic block is. A basic block means whenever the execution enters into this stream of these instructions, there will be no flow control instructions other than the last one in this string. So this is the so-called basic block. Okay? And another condition is there could be two sources of entrance into this string. Okay? So it could come from place A or could come from place B. In other words, before this instruction, the preceding instruction may or may not be executed together with this group. Okay, so this group of instructions must be executed all together or not be executed all together. That's the definition of basic block. And the way you identify a basic block is 2 entrants and 2 exits. Okay, so if this is a basic block, and if my branch will be in effect after 3 cycles, I need to know how many cycles. Then what about if I do this? Number 1, no matter what, I put 3 no OP instructions after the branch if, no matter what. Okay, so this whole thing can now be treated as a basic block. And whether I want to branch or not, this one would be a no OP, no OP, no OP. Okay, you may think I'm doing work in vain, but don't say that, because no matter what, now I don't need to clean up trash. Okay, saving some hardware. Okay, no matter what. That's my step 1 only. Here, I proceed with my step 2. Now, I search through these instructions and try to find some instructions which can be moved to after the branch instruction without affecting the result. If I found one, take it out from this string and replace this no op. If I found another one, I do the same. Replace this no op. Now, can you see these no ops may be absorbed? The size of the branch of the basic block may shrink back. Okay, if I can do this, then they'll be perfect. After that, I may still have some no ops left. Then some more aggressive compiler writer begin to think, maybe I can extend my range of search into the target because more branches are more likely to branch. Okay, or extend the range into my fall through basic block. But whenever you search instruction from here or here, you need to make sure that even if that instruction is executed, but the flow is not as you expected, nothing will be hurt. Okay, result still remains the same. This no op is useless because I say A1 plus register 1 plus register 2 and put the result into register 0, my trash dumpster. Okay, that makes it useless. It can be any instruction, it can be useful instruction, can be instructions that mess things up. Okay, but I need to carefully pick instruction which will not cause any effect. Let it go, let it proceed. Maybe when I say no op, when I say useless instruction, maybe I should say harmless instruction. Does that make you more comfortable? If I can, if it doesn't have any data dependency with the branch if. Like here, I calculate R5 using whatever sources, I don't care. And R5 is not used by any of these instructions between this calculate R5 instruction and the end. Then it certainly can be moved down. without affecting anything. So if I want to use instructions from the target or follow through to fill the no-op slot, then I want to make sure these instructions will not cause any harm. Okay? Okay. If you are not done, then we can do discussion later using Chinese. Okay, so let's get back to this case. How big is a basic block? Typically only 5 to 6 instructions. Very tiny. So how likely can you find the instructions to fill these slots from this basic block? 30%. No more than 40%. Okay. Then what about the possibility from these two? Maybe 20 more percent, 10 more percent. So the possibility of filling this first no-op is about less than 70%, less than 30%, less than 10%, even for 3 no-ops, even for very shallow pipeline. Okay, so this method is smart, but not really practical. Another possibility is we guess. We guess if this branch will branch or not, and then fetch accordingly. So if we make guesses, when should we finish guessing? If I want to guess carefully, I want to take 5 cycles to make my guesses. Nobody cares. You want to make your guess as fast as possible. Usually, only 1 cycle is allowed. Make a guess within 1 nanosecond, within 0.2 nanosecond. Otherwise, your result, I don't want it. Okay, so speed is one super important concern. The second concern is how accurate can you guess in such limited amount of time? Tell me, how accurately can we guess using today's technology? Give me a guess. Give me a guess of how good we can guess. Guess if a branch should branch. 95%, you drop the course. That's too low technology. It's over 98%. Even for commercial users, over 97%. Okay. So, since we can guess so accurately, we don't need to pay attention to this method anymore. Okay. This method is rarely used in new designs. Almost never seen by now. Okay? Okay. We're done with this. With this for you. Okay, example. We use MIPS as an example. MIPS means what? Tell me if you remember. M stands for what? Right, microprocessor without interlocked pipe stages. That's the ultimate purpose of designing a RISC, okay? And they use this for the name of this product or company, okay? So for MIPS instruction set, we categorize all the instructions into 1, 2, 3, 4 types. The first type is register. So your source 1 should be from register, source 2 from register, and this is a destination. And in the real machine code coding, as I told you, the position may be swapped for easy use of immediate bits. Okay? Okay, so these type of instructions are also almost all used for ALU type instructions. Okay? And register immediate can be used for ALU, like you have source 1, source 2, and compute and put the result into destination. Or it can be used for load store. Okay? Base register, offset. If it's a load, result put into here. Okay, so this format can be used for loads and stores or ALU type instructions. Branch operation says branch if equal, branch if greater than, branch if positive, whatever, and you compare the value, the contents of these two registers, and if you want to branch, then this is the PC offset. Okay, and jump, this is an unconditional control flow instruction. So if it's a jump, then this is the target. And the jump is somewhat like direct type instruction, direct addressing mode type instruction. Didn't I just tell you direct is not allowed in here? Right? So how come this can be a direct? Okay, what they do is this. The way they design this instruction is to use the first bit of PC, PC top, appended with this target, and then appended with 2 zeros because these point to an instruction address, okay? An instruction address is always aligned, word aligned. So we have two least significant zeros all the time, okay? So this target goes into this field, and we use the same PC top bit, current PC top bit for the top bit of the direct address. Okay, so we call this pseudo direct addressing mode. So here's the textbook. All the designers have read this textbook when they were in school. And now, as a designer, you need to be able to play tricks. Okay? Tricks not to be found in the textbooks. Like this is a kind of trick they play. Only tricks can make your design, your product, competitive. Question so far? Next. If we have a CPU, define a CPU for me. Tell me, what is a CPU? It doesn't receive instruction. It needs to hunt for its instruction. Right? Go on. That's a very bad start, but it doesn't mean you cannot end with a happy ending.
It does whatever, it does accordingly to the instruction.
Okay. And that's period. Okay, that's all. So it fetches the instruction according to a given value, okay, which is usually stored in PC, or a better name would be instruction pointer, as Intel says. Okay. According to the instruction pointer, fetches it, executes it, and then this process continues, repeats. Okay, that's the definition of a CPU. So in order to do that, a CPU can be divided from the hardware view, one part called controller and the other part called data path. Okay, and the data path has another name called processor. Okay, so processor could mean the whole thing or could mean the data path only. Okay, data path is the part used to store, to perform functions, and I think that's all. Okay, and the functions include input data from outside the CPU, or fetch data from internally and do whatever, and then generate result and transport the result to wherever is appropriate. Outside or internal storage location. Okay, that's what the data path needs to do. So imagine what it has. It has registers, all kinds of registers, R0 to R whatever, stack pointer, instruction pointer, carry flag, overflow flag, whatever. Okay, and then it has adder, subtractor, and or multiplier, whatever. And then all this needs to be connected together using wires. These wires, I call them links, but most textbooks call them buses. Okay, they're nothing but links. If the link has multiple drops, then that's called a bus. Okay? But if a link connects only point to another point, then it's nothing but a pure link. Okay? And then controller, tell me, what does the controller do? If the data path fetches back an instruction, then this instruction will be sent to the controller for analysis, finding out what needs to be done within this instruction cycle. Okay? And whatever needs to be done, commands or control signals are sent out from the controller to the data path to make things happen. Also, commands may be sent to the controller itself. Okay? Also, commands, or maybe not commands, but messages may be sent back to from the data path to the controller, telling it what's happening, what reaction you should take. Okay? So that's the controller. So what's inside of controller? Almost nothing but a decoder. And what is a decoder? Nothing but a nickname for Boolean function. Okay? It just does the Boolean function. This Boolean function can accept all kinds of bit patterns. But those meaningful bit patterns, like the legal opcode, the meaningful bit pattern will generate useful control signals. All the other bit patterns may generate, if this is a Boolean function for opcode decoding, then any not meaningful bit pattern may generate a special signal called invalid opcode, telling everything to stall and invoking maybe some kind of interrupt service routine. Okay, very simple design. Okay, now you all understand what's in the controller? Question? Now you understand the basic function of the controller. Let me tell you more advanced ones. Right, it's nothing but yet another bit input. Okay, and that yet another bit input is treated the same as any of the instruction bit. Nothing but a Boolean variable input. Right? Okay, let's see. What's in the real world? In the real world, the instruction execution is pipelined. So the controller will have to be responsible for the execution of n different instructions in different stages. Got it? Not so simple. Okay, so let's forget about all the other instructions and look only at one. Even for this mere instruction in my pipeline, this instruction will take n cycles to execute. So how can that be realized? This is my controller. what I need to do is, when the instruction comes in, I use a big Boolean function to generate about 100 of the control signals, right? From 32 bits, I generate about 100. In a typical design like Pentium, maybe that number goes up to 200, 300. But anyway, let's use 100 for example. Okay, I generate so many bits. And among these bits are used for execution. These bits are used for memory access. These bits are also used for execution. These bits are used for write back. Maybe I have only 3 groups. These bits are used for execution. These are for memory access, and this is for write back. Okay, I'm not going to use these for now. So what do? I use flip-flops to store them, but send these out right away. Later, next cycle, I use flip-flop to store these bits once more and send these out. And in the final cycle, I send these out. So, at the output gate, maybe I need to use a mux, or maybe not because they all go to different places. Okay? Or if I don't use mux, well, these gates, these bits will go to somewhere in the data path, right? They must go to somewhere in the data path. So maybe at this, at stage execution, I need to somehow nullify these bits such that they will not make any bad things happen in the data path. Okay? By the word nullify, I mean maybe deactivate those components or transportations in the data path. I also need to nullify these if they're not used. So in fact, I'm going to make them go through or be blocked in different time stages, pipe stages. Understand what I say? Okay, because different things need to take place at different times. So I need to let the signals go through or be blocked according to the timing. Clock goes into here. Right, it controls the flip-flops. Also, it controls the gates. Let these open, let these open, let these open. Okay? Got the idea? Let's take care of any instructions in pipeline. Then I have these. Then wrong side. Then I have a, right, I'm sorry, I'm on the right side. Then I have the red instruction coming in, and then the green instruction coming in, and then the yellow, do I have yellow? No. So, when the white instruction goes to here, then the red instruction will be in here, and the green instruction will be in here. Can you see how pipeline takes place when multiple instructions are in the pipeline? Okay, let all the instructions proceed without any obstacle, and every pipeline control signal latch. Latches control signals of different instructions and release them at the right point of time to control the data path. And since all these instructions are in play in the data path, so I don't need this gate anymore. Just let them go out and control the data path. So even for the immediate or source 2, we need somehow to examine the bits in order to determine what we need to do. Okay? But for some very straightforward cases, these bits may be sent directly to the data path. Doesn't need to be decoded. That really depends on your instruction set design. For instance, in the MIPS design, I can send these bits directly to the data path and let the data path and let the control signal to control the muxes or whatever to determine the flow or the usages of these bits in data path. Okay, so maybe these bits don't need to be processed, don't even need to be sent into the controller. They can go directly to the data path. Maybe even these bits, maybe even these bits. Maybe we need only to decode the opcode. Maybe. It all depends on your design. If that's the case, then your decoder becomes very tiny, right? Remember, this is just an example. Okay, OP code. How many bits? Tell me. Whatever. How many bits? Huh? 8? Okay. 8. Okay, for the 8 bits, maybe I use 2 bits to determine whether that's RR, R immediate, or branch or jump. Remember, we have 4 types of instructions in MIPS. Okay, so these 2 would be instruction type. Okay, so for whatever instruction type, let's say register type, I use these bits to specify the instruction. Like for type 00, I have add with immediate or and whatever. However, for type 01, I have load, store, or add with carry. And this is add with immediate, okay, because this is the immediate type, supposedly, okay. And for 10, that's the branch, okay. I have branch always. I have branch if greater. I have branch if positive. I have branch if whatever. And for the 11 type, I have jump. And I have jump and link. Okay, using these bits to specify the instruction of whatever type. And use these bits to specify whether I want to set condition code register, whether I want to do whatever. Okay, then can you see how we design the instruction OP code? Next, the decoder. So the decoder with this 00000, then it activates the ALU to do add, and the source 1 comes from the ALU input 1 comes from source 1, ALU input 2 comes from source 2, and the result writes back to the destination. And you should be able to imagine how we open and close those muxes in the data path design. So we need control signals to the ALU specifying the operation is an add without carry. Okay, sometimes we add with carry. Okay, and the source one is read out from the register file sent through the bus to the ALU input 1. From register file to the ALU input 2. And the result will eventually be sent back to destination register. Okay, open, close, all the muxes and whatever gates. Okay, can you see how this thing is implemented? Okay, so let's continue. The controller. Now you understand controller doesn't have to be a state machine unless, when do we need to use a state machine? Condition number 1, this instruction will take multiple cycles to execute. Condition number 2, in fact, there's no condition number 2. Okay. Condition number 2 is if there are multiple instructions in execution simultaneously. But that automatically implies some instructions will take multiple cycles. Okay. So if we have multiple instructions in execution simultaneously, then we need to orchestrate operations within the entire CPU. Okay, data path then contains some components. The most fundamental ones being the register file, ALU input latches, and ALU, and those links. Okay? And the control signal contains instruction, decode. This decoder decodes the external instruction to generate some internal control signals, and some control signals may be used repetitively for further decoding for the next cycle operation, next cycle operation, and so on. Okay? And we may do partial decoding here, and then do final second stage decoding to generate the real control signals. Okay. So it's nothing but dividing a big Boolean function into 2 smaller pieces. Okay, approaching an ISA. The instruction set architecture defines set of operations, instruction format, hardware supported data types, named storage, addressing modes, and sequencing. Like if an instruction says nothing, then the sequencing will be current instruction address plus 1. Okay? Like named storage R0, R1, R2, R3. Like data type, word type, half word, byte, bit. Like hardware supported, I have ALU, I have shifter, I have whatever. Like instruction format, the instruction is divided into what fields, each one representing for what meaning. Okay, and the meaning of each instruction is described by RTL on architected registers and memory. So if you want to describe what's going on within the CPU, technically, then a kind of language called register transfer language is the best tool to do so. You want me to give you a few examples of this language? Symbols may include R1, R5. Operations may be exclusive OR, and data path, or I should say data links, may mean this ALU output can be routed to register file And comma means this activity is going to take place with this activity in parallel. And semicolon means these activities will occur first, and next clock cycle, these activities will follow. Okay, semicolon means next cycle. Okay, that's the RTL. Does it say the whole CPU structure? Does it say it all? Yes, RTL can say it all. The first cycle of a 2-cycle instruction. Okay, second cycle of that instruction execution. So that's the basic RTL, and it surely can be used for pipeline design. So given technology constraints, assemble an adequate data path. Given technology constraint, such as how many cycles a multiplier take. Okay, given those constraints, then you can put the components together adequately to form the data path. Okay, and architect storage mapped to actual storage. Architected storage may mean PC. So where should you place the PC in your hardware? Is it one of your general purpose register, or is it a particular special purpose register? It all depends on the ISA. And function units to do all the required operations. You want to do AND, you want to do OR, you want to do this and that, then what circuit components may be available for you? And possible additional storage, like we never specify memory address register, memory buffer register in the instruction set, but they may be helpful. Why can they be helpful? Because whatever is fetched back from the memory could be placed in the proper register in following cycles. In other words, not immediately. So you need to have some places to keep them. And these places are not to be seen by the programmer. Okay? And then interconnect to move information among registers and function units. The links, you see the links in the previous diagram. Then map each instruction to a sequence of RTLs. After you have the functional block diagram, try to work each instruction out to see if your implementation or your organizational design is feasible. And then collate sequences into symbolic controller state transition diagram. Okay, so state transition diagram, you see, you have a sequence of RTLs. These RTLs basically only mean what's going to happen in your data path. But then you need to construct a proper state machine, state transition diagram, or finite state machine. That finite state machine is for the controller design. Okay, how many steps do I need in order to accomplish the whole instruction? Okay, one state machine for each individual instruction. And all these state machines should not have any big conflict, such that one controller can take care of it all. Okay? All state machines should look somewhat similar. What do I mean by similarity? Like everyone will have something like fetch, decode, execute, and so on. Okay, every instruction will go through about the same sequence, and then back to fetch. Okay, that can simplify the design of the controller. So once you have the state transition diagram, materialize it. Lower means make it more realistic, down to the logic level, down to the circuit level, down to the physics level. And what control signals should be generated. And then your design is now implementable. Question? How come we lost 2 comrades? And the attendance rate today is not too high. Is that because of the rain? Because of the code? All these cores can be different. If all these cores are different, we call that a heterogeneous design, heterogeneous multi-core. Or they can be all the same and placed equally in computing power, communications, then we call that symmetric multiprocessor. Okay, symmetric means everyone can do the same job equally well, and everyone can access the memory with equal distance, and everyone has the same distance to all of its neighbors. Okay, everything is the same in all aspects. Then we call them symmetric. Okay, SMP, symmetric multiprocessing, is a very important category of multiprocessor design. Why is it important? Because it's easy to program. No matter where you put each piece of your program on this multiprocessor, the result would be the same. See? Much easier to program, to use, but may not be very efficient. For instance, I may not want this. I may want this. So as you can see, this may not be symmetric. Let's do this. This may not be symmetric because this one has only 2 neighbors, yet these 2 have 3 neighbors, okay? The interconnection make them not symmetric, but this could be useful because my program pattern maps well onto this structure. Okay? Or I do this. This is a 2-processor multiprocessor system. Yet one does floating point and one does one does fixed point and one does floating point. Could be very useful, could be very efficient, but they're not symmetric. Okay, so for the 5 steps in the pipeline, fetch, decode, and in the meantime we do register fetch. Tell me, why can I fetch registers even during decoding, even before I know what the instruction this is? Why can I do this? The answer is simple, because the format is so fixed. So if you need S1 and S2, then they come from here. So I always do fetch. What if you don't need these 2 sources? Doesn't matter, just throw them away. Okay? So I always can fetch, and if you need them, I have them available. That's how I can speed things up. Shorten the pipeline length. Execution, or for the loads and stores, I do address calculation and memory access and write back. Okay, and these are the function units we need. These are the links we need, and this diagram shows only the data path, but not the control. Will this work? Sure it will. And the RTL, register transfer language statements, content of PC is used to fetch memory, doing a load, and the loaded result is put into the instruction register. Instruction register is not shown here. Okay? And then PC is incremented, okay, in the fetch. And where's the instruction register? This one is shown. Let's see. Where's PC? Tell me where the PC is. The PC is here. I'm sorry, PC is here. And the instruction register is here. And the memory is here. And the PC gets incremented by 4 is here. Okay, so all these are in the data path. And then what we'll do is we read a register out from here and send it through the mux to the ALU. We read another register, which is source 2, but here we call it temporary register, out also from here, and send it through this mux to the ALU, and perform operation in the ALU, and then put the result back to the register file. Okay? Okay, what's the difference between this diagram and the previous one? See the difference? Let's go back to the previous page. This page is not a good design. Why is it not good? You see, I use this address to fetch memory. And simultaneously, I added to 4. And then feed the result back to the address. And then, after a while, I need a clock to trigger this new PC value in and also the read out instruction into this register. So that takes 1 cycle. And then in the next cycle, I do all these. Does register file need a clock to trigger it? The answer is yes. So if we have this arrowhead indicating it needs to be triggered by the clock, then we also need an arrowhead here. Need an arrowhead here, and need an arrowhead here to indicate they can be triggered by the clock. And in this design, there is only one instruction which can be in play. No other instruction can be mixed in the same circuit. Okay? When do we trigger this? Suppose everything happens at cycle 0, then we trigger this in at cycle 1, and then when do we trigger things in to here and here? We must allow it for some time to do the job, right? So it should be triggered at cycle 2 to determine whether the result is 0, trigger that cycle 2 to wait until the result is generated. And if that's cycle 2, will I get yet another PC plus 4 in? The answer is, of course, according to this design. So when this instruction is finished, what happens? PC becomes PC plus 8, not just 4. Okay? So this design is no good. There may be flaw in it. I don't know. I want you to go through it and find out if there's a flaw. Okay, always you need to do the hands-on job. Plus, if you want to have multiple instructions in the pipeline, we want to pipeline the design, right? So one instruction is here, plus, say this is instruction I, then instruction I minus 1 will be here, I minus 2 will be here, I minus 3 should be here. So can you see? Instruction register, if it sits here, if there's only one instruction register, then there's no way we can keep more than one instruction in the data path. Or say it in another way, there's no way we can keep the control signals for more than one instruction in the pipeline. Okay? So this is the control signal for instruction I minus 1, I minus 2, and I minus 3. Minus more, meaning this instruction is older. Okay? So a pipeline, the design would be like this. Okay, something very interesting is instruction I minus 3's destination register would be used only after this clock cycle. Okay, so when I minus 3 comes in, destination register field is stored here, but it cannot be used right away. It's not like RS1 and RS2. It should be used at clock cycle 5. So I pass it on for one clock cycle and pass it on again for another clock cycle, and then pass it on again for another clock cycle, and then finally I use it here at clock cycle 5. Okay? And our pipeline depth is how many? 5, remember? So if our pipeline depth is 5, then we should have 5 pipeline latches. The first one being here, second here, third here, fourth here, fifth nowhere. Tell me, where's the 5th pipeline latch? Okay, my reasoning is there must be one. Otherwise, the result from the 5th stage can be stored nowhere. So there must be one. Where is it? Where is it? If you tell me, no, there is no such a thing, then I tell you, everything done in the 5th pipe stage will be in vain. Nobody remembers what has been done. Agree with me? Then where is it? Where is it? It's the register file itself. When register file is read, it's nothing but a memory, and a memory can be combinational. If you don't write to a memory, it's nothing but address in, data out, or Boolean in, Boolean out. Okay, so register can be a combinational. It can be viewed as a combinational. That's why we can do multiplication or square root. Using square root as an example, we can do square root using a memory. We don't really need to calculate the result. We simply store the results in the memory and read it out. It's the same as doing calculation, right? Okay, so, but when I need to write the result back into the register file, it needs a trigger. It is now memory storage. Okay? Okay, so the 5th one is here. Got it? And what about this? This one is triggered in every clock cycle. What about this? When is this triggered? Tell me when that is triggered. Right, you're right, you both are right, because it accepts a new stage 2 control signal storage every clock cycle, but for different instructions. Okay, so all these are triggered every clock cycle, no exception. That's why instruction can proceed. It's just like our heartbeat, never stops. Okay. Okay, so instructions get pumped in from the instruction memory. Remember here we have two pieces of memory. One is instruction, one is data. Okay, so instruction gets pumped in continuously. Got it? Okay. I want next page. This page is different. Okay, let's see what happens. Let me erase it all. This and this occur in this stage. This is fetch stage. And this occur in this stage. And this occurs in this stage. And nothing happens in this stage, and this occurs in this stage. Got it? Okay, tell me where A is. See, we have an A, we have a B. Where's A? Where's B? What?
Register 5. Then registers.
Go to the back, stand against the wall. Where's A? Where's B? Give me a smarter guess. A is here, this area of the latch stage, of the stage latch. B is here, okay? Although it's not shown in the diagram, you should know where they are. I said it wrong, I'm sorry. Write to result, where's result? I'm sorry, result is here. Okay, this portion of the pipe latch. And then result to write back is here. From here to here, write back. And write back to register destination is here. Okay, I'm sorry, I didn't see it all. So, cycle 1, cycle 2, plus invisible decoding, okay, in the decoder, and in the controller. Cycle 3, cycle 4, cycle 5. And I'm sorry they used a different convention. Let me point that out for you. Seems like they use this to indicate these two are taking place simultaneously, different from what I told you. Okay, different language, different conventions, doesn't matter. Okay, no signal, no sign means clock proceeds. Okay, so these two take place simultaneously. So we have pipeline stage 0, 1, 2, 3, 4. Usually it's more accustomed to call them 1, 2, 3, 4, 5 rather than 0, 1, 2, 3, 4. Okay, so we now try to look into the design of the controller. During instruction fetch, we do this. During instruction decode and operand fetch, we do this. And after the decoding, we know what type of instruction it is. We know what it wants to do. So from here, we begin to have different streams of instruction execution. If it's register type, then we use these two to do operation to generate a result. Put in the result portion of the pipe latch. And cycle 4, we push this result one stage further down to the write back portion of the 4th pipe latch. Remember that diagram? Check it out in your lecture notes. And then finally, we write that piece of data into my register file in the final cycle. However, if it's register immediate, then maybe we do immediate OPA. In other words, in here, we drop this out. We don't use it. How can we do that? Oh, okay. This still use red. This ALU operand can come from the register file or the sign extended immediate. Okay, the MUX decides which one this instruction should use. And this control signal is from the controller after decoding of this instruction. Okay, it chooses among between the two inputs. So everything else will be the same except for here while comparing these two. And then for the load, we calculate effective address, use it to read memory, and then write the result back. For the store, do we have store? No store? Okay. For the store, we do this. Register source, write to memory, pointed at by R. Okay, for store. And for store, we don't need this stage. Okay, and for jump, we do this, and for branch, we do this. Okay, so all types of instructions have been executed or implemented in our controller. There's a store. So how do you do store? I should leave this to you. Don't let you see this anymore. How to do jump to subroutine. You should do that. And then jump JR. I don't exactly remember what these two symbols stand for. Check your user's manual out.
Unconditional branch.
Whatever, doesn't matter as long as you know what you need to do. You know how to implement it in your design. Okay, nothing but moving data around. Okay, so what's new in here? I don't think there's anything new in here. Okay, so data stationary control. Anyway, here we latch in the 32-bit instruction. Okay, so this pipeline latch capacity may be only 32 bits if there is nothing else to be stored. And here we did do some decoding. Okay, the OP code is sent into here and generated some control signals to be stored in here. So how do we decode? For the 8-bit OP code, maybe we decode it into two groups of bits. One group is used in the execution stage. The other group is used in later stages, memory and write back. And for this group of control signals, they should be fully decoded. But for this group of control signals, they may still be somehow encoded. In other words, maybe eventually I need 20 bits for these and 10 bits for these. So I need 30 bits in total. But maybe here I partially decode them into only 9 bits. To save the width of the data path, only 9. Okay, and then these 9 bits will be decoded into maybe these 20 bits need to be fully decoded to be used in here, right? So 20 plus maybe 4. And these 4 will then be fully decoded into 10 bits to be used in the final stage. Okay, what's the advantage? First, the decoding may be faster. Then it saves the width of the data path. Okay, so partially decoded until absolutely necessary to fully decode it. So finally, let's see a bigger picture. If I have instructions I minus 1, minus 2, minus 3 in the instruction sequence, I minus 1, minus 2, minus 3, plus 1, and so on. Then, if this is instruction I, then the earlier instructions will be further ahead in the pipeline. And at a point of time, say at clock cycle 5, instruction, I'm sorry, I said it wrong. This is I, and this would be I minus 1, minus 2, minus 3. Okay. At this point of time, instruction I might be doing decoding, and I minus 1 doing execution, and this one doing memory, and this one doing write back. Okay. So using such a pipeline diagram, it is easier to visualize how instructions are executed in the pipeline. Pipeline is not quite that easy. Limits to pipelining, I mentioned this to you. There can be hazards. First, there may not be sufficient hardware for all the instructions to use. For example, memory. 2 pipe stages will both need memory. One for instruction fetch and one for data rewrite. So you might want to have 2 pieces of memory for different purposes. Second, data hazard. The result generated by this instruction may not be ready for this instruction to use. You see, result will be properly placed at stage 5, but will be read out at stage 2 of the next upcoming instruction. So timing-wise, this will cause a mistake. Okay, that's the so-called data hazard. Hazard means danger. Something is very fragile, very weak. And mistakes may happen, okay? And control hazard, we mentioned that using a branch if example. Okay, so one memory port will cause data structural hazard, contention. And in order to avoid that, the younger one should yield way to the older one, okay, by delaying the execution of itself by 1 clock cycle. How does it know that? Can it know that in time? Oh yes, this is instruction fetch. So when it wants to fetch instruction at this moment, it already knows that the memory is occupied. So sometimes, in some cases, this situation would be like this. I fetch instruction, assuming that we don't have memory structural hazard. I do decoding, and when I want to execute, I found out that I cannot do that. So I have a bubble here, and then execute, and then memory, and then write back. So you see, sometimes bubble occurs in the midstream of its execution. Okay? So how do you bubble the pipeline? It's easy to talk about it, but how do you do that? The answer is, again, very easy. As long as I don't let things happen, then it's the same as I have inserted in a no-op. Okay, how do I not let things happen? Don't trigger the latches. Let them still keep the old information. Okay, so how to bubble them? By deactivating the clock. Easy. Okay. Okay, speed up equation for pipelining. Cycles per instruction in the pipeline case. When I pipeline, then ideally, every instruction will take only one cycle. But in reality, there could be hazards, so I may need to insert in stall cycles. Okay? Stop cycles. So the speed up compared with a non-pipelined design, is that right? Okay, unpipelined. Okay, so my ideal speed up would be 1 times how deep my pipeline is, times unpipelined cycle time over pipelined cycle time. But in reality, there could be stalls. So if the clock cycle times are the same, then theoretically, the speed up I get from going from no pipelining to pipelining should equal to the pipeline depth. In other words, here maybe 5. Okay, but in fact, there are stalls. So the speed up can never be so ideal. Okay, for simple RISC pipelines, the idealized cycles per instruction is 1. But speed up will become like this. Very simple example. So let's look at a real example. If we have a 1-port memory versus a 2-port memory, machine A, dual-ported memory, we call that Harvard-like architecture. Harvard architecture says we do have 2 pieces of memory, one for instruction, one for data. But in our case, it is, yes, we do have 2 caches, but the main memory is still unified for instruction and data. So it's never real Harvard architecture, but it's Harvard-like. Okay, it's only Harvard-like. Machine B, single-ported memory, but it's pipelined. I'm sorry, but its pipeline, the implementation has 1.05 times faster clock rate. So ideal CPI is equal to 1 for both, but assuming that loads are 40% of the instructions executed, then the speed up of machine A will be pipeline depth over 1 plus 0, because there's no stalls due to structural hazard, okay? And the clock unpipelined over clock pipelined, so the speed up is equal to the pipeline depth. Yet for machine B, the speed up will be, there'll be 40% chance we need to start the pipeline for 1 cycle. And even if the clock rate is faster, you see, single port has faster clock, because dual port memory is more clumsy, so its access time is longer. Okay? So single port memory, even though the clock rate is higher, there may be stall cycles, so the final result is only 75% speed up of the machine A. Okay, that's a very simple example. So any question up to here?